Hey everyone, and welcome. We're about to jump into one of the most powerful ideas in all of machine learning, something that's behind a ton of competition wins and some of the smartest AI out there. We're talking about ensemble learning. The basic idea? It's pretty amazing. You take a bunch of different models, combine them, and end up with a single super model that's way more accurate than any of the individual ones could ever be. So to really get this, let's start with a question for you. Imagine you've got a really tough, high-stakes problem. Who do you call? One single brilliant genius? Or a whole team of different experts, each with their own unique viewpoint? Yeah, most of the time, you'd bet on the team, right? Their collective wisdom just wins out. And that, right there, is the big idea behind ensemble learning. We're not just building one model, we're building a whole dream team of models. Okay, so here's what we've got on tap. We'll kick things off with why we even need ensembles. Then we'll get into the big three techniques: bagging, boosting, and stacking. After that, we'll jump from theory into some actual Python code, and we'll wrap up with some best practices so you can really nail this on your own projects. All right, let's dive right in. Look, to really get why ensembles are such a superpower, you first have to understand this one core challenge that every single machine learning model runs into. I don't care if it's a simple regression or a massive neural network, they all face this problem. It's kind of the central struggle of all of machine learning. So here's the formal definition. We take a bunch of individual models, which we often call weak learners. Now, weak doesn't mean they're bad. It just means that on their own, they might only be a little bit better than just guessing. But here's where the magic happens. When you combine them in a smart way, all their individual weaknesses kind of cancel each other out, while their strengths add up. The result? You create one single, strong learner that is just incredibly powerful. And this brings us to the main villain of our story, the bias-variance trade-off. You can think of this as a tightrope that every single model has to walk. On one side, you risk being too simple and missing the real patterns. On the other, you risk being too complex and basically memorizing noise. Trying to find that perfect balance with just a single model, man, it is really tough. This lays it out perfectly. On the left, you've got high bias or underfitting. The model is just too simple, it misses all the important details. Then on the right, you have high variance or overfitting. And this is like that student who just memorizes the answers for a test. They'll ace the practice questions, sure, but throw them a new problem on the real exam and they're totally lost. They can't generalize. This whole trade-off is exactly what ensemble methods are designed to solve. Okay, so let's introduce our first hero in this story, bagging. The easiest way to think about bagging is as the democratic approach. We're going to build a diverse committee of models, and then we're just going to let them vote on the answer. And this, as you'll see, is an amazing way to deal with that high variance overfitting problem. The name, bagging, actually tells you exactly what it does. It's short for Bootstrap aggregating. Bootstrap is the clever way we create a bunch of slightly different training sets from our original data. And aggregating, well, that's just how we combine all the predictions at the end. Let's walk through it. So here's the process, step by step. First, bootstrapping. We take our main training data and create a bunch of new, smaller data sets by sampling from it with replacement. That with replacement part is super important. It means some data points might get picked multiple times for one sample, and some might not get picked at all. This gives each model a slightly different view of the data. Next, we train a model on each of these samples, and we can do this all in parallel at the same time, which is really efficient. Finally, we aggregate. If we're classifying, it's a majority vote. If we're predicting a number, like in regression, we just average the results. Simple as that. So the big takeaway, the number one reason to use bagging, is to reduce variance. But why does it work so well? Well, think about it. Each individual model might be a little bit overfit to its own little data set. It might be picked up on some weird noise. But since they all saw slightly different data, their mistakes are going to be different. They won't all make the same errors. So when you average all their predictions together, those random individual errors just kind of cancel each other out. What you're left with is a much more stable, reliable prediction. And of course, we can't talk about bagging without mentioning its celebrity superstar, the random forest algorithm. If you've done any ML, you've heard of this one. And it is exactly what it sounds like. It's a whole forest of decision trees. Each tree gets trained on a different bootstrapped sample of the data. Plus, it adds another layer of randomness by only looking at a random subset of the features. All this randomness makes the trees really diverse, which makes the whole forest incredibly robust. It's one of the most popular algorithms out there for a very good reason. All right, on to our second major technique, boosting.
Now, if bagging was like a democracy, boosting is totally different. It's more like a line of specialist apprentices, where each one learns from the mistakes of the one before it. It's a sequential process, and the whole idea is to laser focus on what the model is getting wrong.
Yeah, the key idea is sequential learning. The master-apprentice analogy is perfect. The first model makes some mistakes. The second model comes along, and its main job is to fix those specific mistakes. Then the third model focuses on the errors that are still left. Each new apprentice is trained specifically to correct the errors of its predecessor. It's all about turning weaknesses into a collective strength. So how does this actually work? Well, you start with a really simple, basic model. It's probably not very good. Then you look at all the places it got things wrong. You take those misclassified data points and you give them more weight. You're basically shouting at the algorithm, hey, pay more attention to these ones. Then you train the next model, and it's forced to focus on those tough, high-weight examples. You just keep repeating this process, with each new model cleaning up the remaining errors. It's a slow, steady, incremental path to a super accurate model. So remember how bagging was all about reducing variance? Well, boosting's main goal is to reduce bias. And it makes sense, right? Because it just keeps hammering away at the examples it gets wrong. The final model ends up being really complex and fitting the training data extremely well. It learns those tricky, intricate patterns that a single model would probably miss. This is a head-on assault against underfitting. And I gotta tell you, boosting has produced some of the most legendary powerhouse algorithms in all of machine learning. You see these names winning online competitions all the time. You've got AdaBoost, the OG of boosting, gradient boosting machines, and of course, the kings of the hill, XGBoost and LightGBM. These are absolute must-know tools for any data scientist. Okay, this table is a perfect showdown between the two. Let's break it down. Training. Bagging is parallel, fire up all the models at once. Boosting is sequential, one after the other. Main goal. Bagging is your go-to for fighting high variance or overfitting. Boosting is for fighting high bias or underfitting. How they see the data. Bagging uses random samples. Boosting sees the entire data set, but it keeps changing the weights. And finally, how they make a decision. Bagging is a pure democracy. One model, one vote. In boosting, it's a weighted vote. The better models get a bigger say. It's two completely different philosophies. So we've had the Democratic Committee with bagging and the team of apprentices with boosting. But what if? What if we could go one level deeper? What if instead of just a simple vote, we actually trained a manager model whose only job is to learn how to best combine the outputs of our other models? Well, that's the genius idea behind our third method, stacking. Yeah, stacking, or sometimes you'll hear it called stack generalization, really takes this whole ensemble thing to the next level. We're not just averaging or voting anymore. We are learning the best possible way to combine predictions. We do this with a new model called a meta model or meta learner that sits on top. Its only job is to look at the predictions from our other models and learn how to make the best final call. Now, the process is a little more complex, but it's super clever. First, you train a bunch of different base models, and I mean different. Maybe a random forest, an SVM, a simple neural net. Diversity is everything here. If all your models are the same, the manager has nothing to learn from. Then you have those models make predictions on some data. And here's the crazy part. You take those predictions and you use them as the input features for a brand new data set. Finally, you train your meta model on that data set. It learns to look at the predictions and say, okay, in this situation, I trust the random forest more, but over here, the SVM is probably right. It's learning the strengths and weaknesses of your team. Okay, enough theory. I know that was a lot, but the best part is you don't have to build all this from scratch. It's actually really easy to implement these days. So let's jump into some Python and see how to do this with the go-to library for this stuff, scikit-learn. Check this out. This is the code for a bagging classifier. It is super simple. You just import bagging classifier, tell it what base model you want to use, like a decision tree, and then you set the key hyperparameter and estimators. That just means how many models do you want in your committee. That's pretty much it. Scikit-learn does all the heavy lifting of bootstrapping and voting for you in the background. And here's the proof in the pudding. This chart says it all. On the left, you've got a single decision tree. Its accuracy is, okay, maybe 85%. But then you wrap that same model in a bagging classifier, create a forest of them, and boom, look at that jump to 94% accuracy. That is the power of reducing variance right there. Just a couple lines of code gets you a way more powerful model. And what about boosting? Just as easy. Here's the code for AdaBoost classifier. The setup looks really similar, right? But you'll notice a different hyperparameter here, learning rate. This is a really important one for boosting. It basically controls how much impact each new model has. A smaller learning rate means it takes smaller, more careful steps, which can often lead to a better final model. Last but not least, here's stacking. Okay, the code is a little bit more involved, but it makes perfect sense when you look at it. You just create a list of your base models. That's your dream team. Then you specify the final estimator. That's your manager model. You just plug those into the stacking classifier, and again, scikit-learn handles the whole complicated two-stage training process automatically. Pretty awesome. So there you have it, a whole new toolkit of powerful models. But you know what they say, with great power comes great responsibility. Knowing what these things are is one thing, knowing how and when to use them effectively is another. So let's wrap up with some essential best practices for the real world. And this is really why this stuff is so important to know. This isn't just theory. Ensembles are the workhorses of modern machine learning. They're the secret weapon that wins Kaggle competitions. They're what banks use to detect fraud, what doctors use to help predict diseases, and what cybersecurity experts use to find hackers. In these fields where every little bit of accuracy counts, ensembles are absolutely critical. But, and this is a big but, they are not a silver bullet. You gotta understand the downsides. For one, they can be black boxes. It can be really hard to explain why a complex ensemble made a particular decision. They're also expensive. Training 100 models takes a lot more time and computer power than training just one. And remember, if your data is garbage, your fancy ensemble model will still give you garbage results. So what are the keys to success? Number one, always start with your data. Good feature engineering beats a fancy model any day of the week. 2, make sure your models are diverse, especially for stacking. You want them to have different strengths and weaknesses. 3, you have to tune those hyperparameters. The defaults are just a starting point. And finally, use cross-validation. It's so important, especially for stacking, to make sure you're not fooling yourself about how well your model will perform on new data. Okay, let's wrap this all up in a neat little package. Here's the cheat sheet. If your model is overfitting and has too much variance, think bagging. If your model is underfitting and has too much bias, think boosting. And if you have a bunch of pretty good diverse models and you want to squeeze out that last ounce of performance, think stacking. That's your toolkit. So there you have it. You've met the team of heroes. You've seen the democracy of bagging, the sequential learning of boosting, and the clever manager model of stacking. Now, the only question is, what problem are you going to solve with your new ensemble? The power is in your hands. Thanks so much for watching, and go build something amazing.